So now we're going to learn a method of integration using inverse trig substitutions. And I can tell you that the name is a little bit misleading because we're not actually going to integrate trig functions. We already did that before when we looked at the power being either even or odd on a trig function and using identities to work our way through. Inverse trig substitutions are actually used when what you want to integrate is a rational number or a rational function. Now I'm going to go off the page down here, and I don't actually suggest that you write this next thing down. I'm just going to show you why we're going to do what we're going to do. If I asked you to integrate 1 over 4 minus x squared dx, the first thing you might think is, oh, this is a u substitution with a natural log integral, and that would be a value, that would be exactly what I'd want you to think first. Always go to the easiest possible method first. So if I do the substitution, u equals 4 minus x squared, then du is negative 2x dx. Solving for dx, I get du over negative 2x equals dx. So now I have something to plug in for my dx, all of this, and I have something to plug in for my u, or excuse me, for my 4 minus x squared u. So let's go ahead and make that substitution. Well, that gives me 1 over, well, 4 minus x squared is now u. That looks good to me. And then my dx is going to become du. That also looks good because I like to have a differential that is in terms of the same variable I'm working with, over minus 2, not a problem, constant multiple I can pull out, x. Darn it, I'm not supposed to still have an x. If I'm integrating with a substituted u, then I want to be rid of all of my x's. No worries, you might think. I'm just going to go up here and I'm going to solve for x. So this would be integration using substitution with a change of variable. So x equals the square root of, and it would have to be plus or minus the square root, that makes it complicated, of 4 minus u. So if I plug that in, then I'm looking at the antiderivative of 1 over u du times the square root of 4 minus u. And that is ugly. What we wanted with the u substitution, particularly the change of variable u substitution, is to take one great big rational number and turn it into a bunch of little tiny ones that I can integrate separately. So this clearly isn't the method for this problem. When that happens, the first thing that you want to think of is the inverse trig substitutions. So let's write the same problem out again. If I'm, in this case, I'm looking at 1 over 4 minus x squared dx. Now, there are 3 different considerations to make. If the rational number contains a part that looks like one of 3 different ifs, then you'll be given a then for what to use. And the one that looks like this is written a squared minus x squared. So if you get something in the form of a squared minus x squared, then the substitution you want to use is the sine of theta. You want to use a sine substitution when this form is in your problem. How am I going to use a sine substitution? Well, we have to create a triangle that has this part in it. So let's do that. Well, sine of theta is always the opposite over the hypotenuse. And I'm going to give you a little hint. Whenever we're doing this, the denominator is always the number that is not the variable. A is going to be an actual value in these problems, 9, 12, 16, whatever. A is going to be an actual number, and that's always the one that goes in the denominator. So when I put together my triangle, it looks like this. Well, if it's a right trig triangle with theta, then the sine of theta, the opposite of theta, is here, and I'm going to give that the x, the other value, And the hypotenuse is a, because the hypotenuse is in the denominator of the sine function, and it's always the value that has an actual numeric value. So then I have to solve for my other side. So then b, I don't need a label for it, but b would have to equal, in this case, a squared minus x squared, if I just do the Pythagorean theorem. Okay, well, we're close, because this is the square root of exactly what I'm looking at here, where a would be 2, 2 squared minus x squared would be my adjacent side. So I would have a trig triangle to describe this rational number. However, I don't have exactly the same thing. So no worries, because remember, you can always square all the sides of a similar triangle. So I would have a triangle that reads x squared, a squared, that's what I have right there, and then the adjacent side would be a squared minus x squared, which is looking dangerously a lot like what I have there. So this is the triangle setup. This is the justification for being able to convert this rational number into a trig function. And if we do that, and luckily you'll have a rule, the rule says if it looks like this, make this substitution. So let's make that substitution. Since I have two triangles to choose from, and I'm looking to substitute for x squared, I'm going to go ahead and choose the x squared version. So that means I'm looking for the sine of theta equals x squared over a squared. But if this is an x squared triangle, that means the sine is also squared. All parts of the triangle are squared. Because, and that makes total sense, if I'm looking at a ratio sine of theta equals x over a, if I square this side, I have to also square this side. So sine squared of theta equals x squared over a squared. So then I can solve for x squared. X squared equals a squared sine squared theta. So that gives me my substitution for x squared. 4 I don't need to substitute for, but I do need a substitution for dx, which means I need to differentiate the original. Before I do that, I'm going to simplify it. Why differentiate with a square when I don't have to? So this actually is x equals a sine theta, so dx equals a cos theta d theta. And now I can do a substitution, because using a triangle, taking this value, putting it onto a trig triangle, I'm able to rewrite this rational number, rational function, as a trig function, and from there I can simplify it. So I'm going to do that exact same problem as an example. Only this time I'm going to do much less of the explaining how we got there and much more of the just doing it. So I'm looking for the antiderivative of dx over 4 minus x squared. So I know that this is a squared minus x squared form. I want to use sine of theta, and I know that sine of theta equals x over r, which means the denominator is r, so my a value is my hypotenuse. R is the hypotenuse. I probably should have used, because I'm used to using that, opposite over hypotenuse. It doesn't matter. It's just probably makes a little bit more sense at this stage of the game. So my hypotenuse has the a value. I set up my triangle where a equals, in this case, 2, because a squared is 4, and then x is the opposite, because I'm talking about the sine triangle. I'm using sine. And so the other side, and I'm just going to pull it off of here, is the square root of a squared minus x squared. And normally I don't go ahead and do the squared triangle, just because sometimes I don't need to know what the adjacent is. If it disappears in my work, then I'll never have to go back and do it. So at this stage, I'm just going to stop here, and I'm going to say then my substitution is sine of theta equals x over 2, so x equals 2 sine theta, and when I square that, I can rewrite my integral as, I need a derivative, dx equals 2 cos theta. So in the numerator, for dx, I'm going to have 2 cos theta d theta. And in the denominator, I'm going to have a squared, which is 4, right? 2 squared, minus x squared. Well, this is x, so x squared is 4 sine squared of theta. So I'm going to put in x, not x squared, 4 sine squared theta. So now we're basic simplifications and trig identities all the way. I'm going to pull the 2 out. So I'm left with cos theta d theta. And in the denominator, I'm going to pull a 4 out. So I'm left with 1 minus sine squared theta. I instantly recognize that as a Pythagorean identity. And so I have the cos of theta d theta, and I'm going to go ahead and write it out because it's been a little while since we've seen them. Sine squared theta plus cos squared theta equals 1. So 1 minus sine squared of theta equals cos squared theta. Well, there's a simplification right there. So I have 1/2 times, I have cos to the first power in the numerator, second power in the denominator, and I'll go ahead and write it out instead of taking a shortcut. That's 1 over cos theta d theta, which equals 1/2 times, I'm looking for the antiderivative of secant theta d theta. And the antiderivative of secant is not one we can arrive at on our own. It comes from a trig table, and you will find the antiderivative of secant theta on the extras tab on my web page, where I have some resources posted. And you'll find that this is 1/2 times the antiderivative of secant is the natural log of absolute secant theta plus tan theta, and of course plus c. Now, at this stage of the game, most of us think we're done because we've done a lot of work, but we are not done because this is an antiderivative in terms of theta, but we want an antiderivative in terms of the polynomial function, including x, or of x. So this is where we go back to our triangle. First, let's look at what is secant theta. Well, secant theta is the inverse of cosine theta, so this is the hypotenuse over the adjacent, and tan theta, TOA, is the opposite over the adjacent. So we're going to plug in values from this triangle that are secant theta and tan theta, which will bring us right back to our values in x. First, let's go ahead and substitute a squared. We know that a is 2, so this would be 4 minus x squared. That'll save us an extra step in the plugging in stage. So let's go ahead and insert our new values. 1/2 times the natural log, the absolute value, hypotenuse is 2 over square root of 4 minus x squared, plus the opposite is x over the square root of 4 minus x squared, plus c. And then I definitely should clean up. I normally at this stage wouldn't do a lot of extra algebra. If I needed to, I would, but I tend to like things in their rough state because I can always go where I want to go later. But we do have the same denominator, so let's combine 2 plus x over the square root 4 minus x squared plus c, and call it a day. So I had intended to go on and give you the other 2 types of rules, but I think this is far enough for today. So really, this lesson is inverse trig substitution involving sine theta, but we will we'll deal with tangent and secant in our next lesson.